Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using, as far as possible, only the standard libraries and the SDL2 library so that we can display results in a window. Now, in this particular episode, we're going to be looking at normal maps, and I suspect this is going to be the first of a two-part, possibly three-part mini-series looking at normal maps and how we can use normal maps and what they are. What I want to focus on today really is the very basics of what normal maps are and how they work, and the very basic sort of setting up the core infrastructure within our code base that we need to be able to actually work with normal maps in a more interesting way. We will go on to implement a very basic normal map. So that's pretty much it for the introduction. Just quickly before I jump into it, say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please do consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Right, without much further ado, let's jump into it and let's have a look at normal maps. Okay, so this is now episode 17 of our series on writing a ray tracer, and as I've just said, we're going to be looking at normal maps. I want to start really with taking a quick look at what really normal maps are and what we can use them for and that sort of thing. So this example animation that you can see going on here, we can see that we have a plane with a marble pattern on it, and we've got the three balls there and the normal of the plane shown by the purple arrow. And as the animation plays, we can see that we have this ripple waving effect going on across the surface. Now, this is not geometry. This waving effect is created simply by perturbing the surface normals, which you can see shown by the green arrow, and you can see that oscillates back and forth as the waves pass by it. So normal maps are a really great way of adding surface detail without having to add geometry. Adding more geometry, creating a surface like this that actually had waves in it, yes, we could do that, but it's really quite expensive in terms of rendering time and everything else. And I mean, there are situations where you don't have a choice and you would have to do it that way, but for situations where you don't, particularly when the surface detail is relatively small, then simply using a normal map can be a really effective way of adding detail without adding geometry. So similarly, this is just another animation that I've done, and this shows the same wavy normal map, this time applied to a glass sphere. So you can see that as well as affecting reflections and illumination, the normal map is perturbing things like refraction as well, which is exactly what we would expect. This is just another demonstration, again a normal map applied to the plane, and in this case you can see that we're creating what looked like something approximating ripples out from a pond, and this is actually a sinc function that I've used to perturb the surface normals, or more precisely I've used the derivative of the sinc function to perturb the normals, creating the effect of a sinc function causing waves. But we'll talk about that in a future video. That's not something we're going to talk about today. Okay, so how exactly does this work? Well, I've mentioned about surface normals, and all of the objects and everything that we're creating in our scene, every object has a surface normal, and the surface normal is simply a vector that is perpendicular to the surface at any particular point, and you can see that here. So I've got an array of I've got an array of 5 different objects here, and I've shown an example of its surface normal with a purple arrow, as you can see, and we can sort of move those purple arrows around the surfaces, and you can see that wherever we look on the object, the normal is always going to be exactly perpendicular to the surface at that point. So that's what the normal is. Now, the normal is used for everything. It's used to calculate the shading, so we use it to calculate the angles between the surface of the object at that point and the light, which we then use to calculate the intensity. It's used for reflections, it's used for refraction if we have transparent objects and everything like that. So what we can see is if we disturb the normal, if we perturb the normal in some way, then we are going to affect all of those things. We're going to affect the shading, we're going to affect reflections, and if we have it, we will affect refraction. And if you think about it, at the moment, a scene like this is sort of the sort of basic scene that we can create at the moment, and all of these objects, it looks okay, but everything looks very, very flat. In real life, surfaces are never really that perfectly flat. I mean, they can be highly polished glass or mirrors or something like that, but most objects do not have perfectly smooth surfaces, so it's quite unrealistic. So it's good to have a technique that allows us to put some detail, some texture into the surface beyond simply a pattern. And just as a quick example of sort of how that works, I have this animation here. We have the plane on the left is physically tipping to the left and then to the right, and you can see that the surface normal is shown by the purple arrow, and the plane on the right is not moving. But what I'm doing is simply perturbing the normal to be the same as that of the plane on the left, and you can see the effect that it has as the plane tips to the right. You can see for the right-hand plane, the surface normal stays exactly the same because the surface isn't moving, but we are adjusting the normal according to the perturbation, and you can see how it distorts the reflections and changes the illumination on the plane. Now, of course, it's not exactly the same, and this is a really important point. So in this situation on the left, where we've actually rotated the plane, we see that the sphere in the reflection stays spherical. It's moved to the side, it's moved in this case to the left as the plane has rotated to the right, but it's remained spherical. Now in the case on the right, what's happened is things have stretched out and become distorted. Now the reason they're different is of course because in the situation on the right where we've changed the normal, we haven't actually changed the position of anything. So we don't expect it to literally be exactly the same. And this is a really important point because it means that adjusting the surface normals in this way works very well for small perturbations, where small details and things. It's not really a good technique where you've got very large things. So in this case, I mean, I've tilted the plane by probably about 30 degrees there, and you can see very clearly that that does not yield the same effect simply by perturbing the surface normals, or rather perturbing the surface normals does not yield exactly the same effect. Okay, so there are limitations to the technique in terms of what we can do. You know, it's very, very effective if the perturbation is very small. We can use to increase surface detail in that way. You can imagine if you have many polygons or something like that and you disturb the normal of them all separately, then you could achieve interesting results. The final animation shows just an example. There's a little bit of a complexity to this that we have to consider. So in this example, we have again a plane with checkerboard floor, the classic ray tracing example of the checkered board floor, and we have the surface normal that we are disturbing according to the vectors shown in green. And so you can see that as the normal rotates around, we are effectively adjusting the normal in the UV plane, okay, or that's actually the equivalent of the XY plane in this coordinate system. And you can see the reflections in the plane are adjusting as they should. And so we can see that when the surface for whose normal we want to adjust is perfectly horizontal, as in this case of the plane here, then this is really very easy. We can just adjust the normal according to these two vectors. So we have a vector in x and we have a vector in y, and we can set those to anything and adjust the normal accordingly, and everything works, okay? Now the problem comes is, what if the surface that we want to alter is not perfectly horizontal? Okay, and let's consider that. Let's rotate our plane by 45 degrees, something like that, okay? And now you can see that if we were to displace the normal vector, so the purple arrow is the normal vector, if we were to displace the normal arrow according to those same vectors, you can see that we're going to move along in the x-axis like this, and you can see that that is not going to yield the effect that we had before. What we need is a way to rotate the vectors that we are displacing our normal along according to the new coordinate system, so that we are then achieving the same effect. Now we're going to do that using our friend from vector math, the dot product. Okay, very useful. And this is something that we have looked at before when we talked about camera geometry way back in episode 2, I think it was, or possibly episode 3, I forget, but the episode on camera geometry. So you can go back and have a look at that, but I am going to talk about it when we come to look at the code. So what we're going to do is use the vector dot product to allow us to calculate exactly what the vectors that we want to make our displacement to the normal along. And effectively what that equates to is calculating the tangential plane. Okay, so the normal is the vector that is perpendicular to the surface of that object, but the axes by which we want to disturb the normal or perturb the normal are the vectors in the tangential plane, so the plane that is the tangent to the object or to the surface at that point. So we will look at that when we come to look at the code. So I suggest we do that now. Let's jump into it. Let's have a look at the code. Let's go and see how we can actually go about implementing surface normals in our C++ code. To start with, I'm here at my terminal window. Just have a look at our code base. If you've cloned the repository from GitHub or you've been very diligently following along, you should have something like this already. If we go into the QB Raytrace subfolder or directory, we can see that I've created a new subfolder here called QB Normals, and we're going to put all our normal map implementations into there. If we go into QB Normals, and you see we have a base class, normal base.hpp and .cpp. I've created a very simple constant normal map that simply applies the same displacement everywhere. I'll show you the code for that, but I'm not going to show any examples of using it because it's frankly not very interesting. And I've also created for this episode just a very simple normal map called simple rough that will apply a simple random perturbation to every point on the surface. Okay, it's a good way of approximating a rough surface, but it's not particularly interesting, but it's adequate, I think, for this first part of this mini-series. Okay, so that's what we're going to be looking at. So let's go back to the root folder. Okay, let's jump in and have a look at the code for our base class. So here we are, this is normal base.hpp. So as always, I'm creating a base class, and then other classes that actually implement specific normal maps are going to inherit from this. That is the way we've done it for textures and for our primitive shapes and everything else. We have our include guards, as always. We're not going to talk more about those. I've talked about that kind of thing extensively. We bring in QB matrix and QB vector from our linear algebra library. And we're bringing in texture-based.hpp, which we're not going to use at the moment, but when we come to talk about that in a future episode, you'll see why. So, as always, we have our QBRT namespace and then our normal sub namespace. I'm not a fan of sub namespaces, but I think two levels is not necessarily such a bad thing. And we declare our class normal base, and then we have our constructor and our destructor, remembering of course to declare our destructor as virtual because we're going to be inheriting from this. We have a function to compute the perturbation, okay, so that will compute how much we're going to disturb the normal by at a particular point. So it accepts as input a vector representing the normal that we want to perturb and the UV coordinates at that position, okay, and it returns a QB vector double object. It's virtual because we're going to override it for every instance. We have a function that actually applies the perturbation. This is not virtual because it will be the same in every case, so we can simply put it in our base class. It accepts as input the normal vector and the vector representing the perturbation, and it returns a new vector object representing the new normal. We then have a function to set amplitude, a function to set the transform, exactly the same as we use for the texture maps, so we can apply geometric transforms with the translation, rotation and scale to the normal map in the same way we would do a texture. And we have a function to apply the transform to a given input vector, the same as for scale maps. And then we need to store our amplitude scale factor, which we simply store as a public member variable. And we have a private member variable here to store the transform matrix, and just that, which is initialized to the identity matrix. Okay, and that is everything for normalbase.hpp. Let's go and have a look at normalbase.cpp. Okay, so normalbase.cpp, we of course hash include the HPP file we've just talked about. We declare our constructor and destructor. We don't need any code in those. We have our function to compute the perturbation. Now this is the base class from which everything is inheriting, so we don't do anything in here except return the default response, which is simply 0, 0, 0. So we simply return a QB vector object initialized to 0, 0, 0. We have a function that actually computes the perturbation. Now this is where we need to compute the axes about which we're going to perform the displacements, okay, as I just talked about in the introduction. So the first thing that what we do is we need to define an up vector. So if you think about the classic right-hand rule for vectors, okay, if we have our normal vector, and we want to calculate a vector that is perpendicular to that, we need to know one other vector, which we call the up vector. So we can define that to be in any arbitrary direction, but usually up is the way, hence the name. And then simply wherever our normal vector is, we can then take the cross product of the up vector and the normal vector, and it will give us a vector that is perpendicular to those. Okay, if you imagine those two vectors make a plane, and then the vector we want is the one perpendicular to that plane. Okay, so we do that using the cross product. It's pretty simple, but we define an up vector initially as being up, but we need to check if the actual normal vector is very close to the up vector, then it won't work. So if our normal vector is pointing nearly straight up, then there's no point having an up vector that points straight up, in which case we create an up vector that points in the positive x direction. Okay, so that's what we're doing here. We simply check the z component of the normal. If it's very close to 1 or very close to -1, if it's greater than 0.99 or less than minus 0.99, it should never be greater than 1 because this vector should always be normalized. So that's okay. And in that case, we define our up vector as being in the positive x direction. Otherwise, we leave it in the negative z direction, which in our coordinate system equates to up. We're then going to compute the axes about which we're actually going to perform the perturbation. So the first one, the PV, which we're calling PV, we simply get from the cross product with our up vector and normal. So that's pretty straightforward. And then we normalize it. And then we're going to calculate PU as the cross product of the normal vector and PV that we've just calculated. And then we normalize that. And for whichever direction our normal is pointing in, combined with our up vector, this means that we can generate two vectors that are perpendicular to the normal, that therefore represent the tangent plane and are therefore the axes about which we want to perform the perturbation. Okay, and then all we have to do once we've got that to apply the perturbation, the new vector, which we've called output, is simply equal to the original vector normal plus Pu from here, multiplied by the x element, if you like, or perturbation.getElement0 of the perturbation, plus PV multiplied by the y component of the perturbation. Okay, you can see how that's working. So the first and second elements of the perturbation vector describe the displacements in u and v respectively, where u and v are arbitrarily defined according to the calculation we've just done. And then simply there's a final component we simply apply to the normal, because this is a displacement in the same direction as the normal. Okay, so that's it. It's really very simple. We then just normalize that to make sure everything stays normalized, and we return the output. And that is everything that we need to do to actually apply a perturbation to a normal vector. Okay, we then have a function simply to set the amplitude. It simply sets amplitude scale. We don't need to use that because we defined amplitude scale as public, but never mind. We have our function here to apply the geometric transform. Now this is exactly the same as we've talked about for textures. Okay, so it accepts an input vector and it returns a vector. It simply makes a copy of the input vector and modifies it to have 3 elements. Because of course it has to have 3 elements because our UV space is 2-dimensional. We're going to apply homogeneous transform in homogeneous coordinates. I've talked about that, as I say. Go back and look at the episode on UV space, UV mapping and textures to understand more about how I've implemented this there. And then we simply apply the transform and return the output. And we have a function to set the transform matrix. Again, I talked about that when I talked about textures. I don't want to go over that right now in this episode. As I say, go back, look at the episode on UV mapping, where I talked about that in much more detail. Okay, that is everything for our base class to handle normal maps. So let's have a look at how we could go about a very simple implementation. Okay, so this is constant.hpp. Now this is a really boring example, but it helps just to show how we can actually implement something. So in the HPP file, we declare our class called constant. It inherits from normal base that we've just talked about. We override our virtual destructor, and we have our constructor. We override the compute perturbation method for the specific implementation, and we have a specific displacement that we're going to store in a public member variable. That is it for the header file. Really simple. Let's look at the CPP file. Okay, so constant.cpp, obviously we hash include constant.hpp. We don't need anything in our constructor and destructor, and we need basically just one line of code in the compute perturbation function that simply returns perturb normal of normal and the displacement that we've stored, the member variable displacement. So this is calling perturb normal that we just talked about from the base class. So that will compute the UV axes and will apply the displacement vector to the normal according to those UV coordinates, those UV axes at the particular point that we're interested in. And that's it. That is a very basic example of how we can go about implementing a normal map. Now, let's have a look how we could do something a little bit more interesting than that. Okay, so this is simplerough.hpp. This is designed to be probably the most simple normal map that we could do that actually produces some kind of vaguely interesting result. So the header file is very much the same as we've just seen for constant. We declare our class name, simplerough. It inherits from normal base. We have our constructor and destructor, and we override the method to compute the perturbation. The only thing that's different here now is we're storing in privately a shared PTR, shared pointer, to a random number generator. I'm using the Mersenne twister algorithm to generate random numbers. Okay, right, we'll see more about how that works when we come to look at the CPP file, so let's do that now. Okay, here we are, simplerough.cpp. So, first thing that we do, obviously hash include the header file we've just talked about, and now in the constructor we're going to set up the random number generator. So every time an instance of this class is created, it will set up and initialize a random number generator. So we do that using std::: random device, set up random dev, and we can then use that to create a seed sequence. Okay, you don't have to use a seed if you want it to be the same every time. You could put in a fixed value here, or you could simply leave it out. And we configure m_p_random generator because it's so m for a member variable, p for a pointer. Okay, it's not a naked pointer because we're using modern C++, of course. And we use std make shared to create an instance of the MT19937 Mersenne twister algorithm initialized with the seed. And that is what we need in the constructor. We don't need anything in destructor because we're not using naked pointers. Okay, very important. Now we need to modify the compute perturbation method, and what we do is we create a uniform real distribution called randomDist between minus amplitude scale and plus amplitude scale. So that's going to return real numbers, floating point of double precision between these two values. Okay, and then we simply generate three random numbers, x, y, and z, calling randomDist and passing to the random number generator. Now, of course, m_p_randgen is a pointer. It's not the thing itself. So we have to put the star first to mean that we want to pass the thing itself, not the pointer to the thing. Okay. And that's it, actually. And then we simply put those together into a vector that we call perturbation, like so. And then we simply call the perturb normal function from the base class with that perturbation and the given normal vector. And that's it. That's really everything that we do. And what that will do is create a random perturbation at every point on the object. So it will create a rough texture, which will look a little bit interesting. And it's the example we're going to see in just a moment. Okay, so before we actually look at that, we just need to look at how we can actually make these normal maps useful as part of our ray trace. And first part of that is to look at the make file. So as people following my channel will know, I'm using gmake to compile all of my builds, and so all we need to do is, because we've added a new directory, qbnormals, or a new folder, we simply need to add this line here in the make file to make sure that it scans in the qbnormals directory to look for any CPP files that need to be recompiled. Okay, that's the only change we need there, very simple. The way that I've gone about implementing my normal maps is that I want them to be part of the material. So the material classes form the base of everything, and in the way the code is structured for this ray tracer, we add textures or assign textures to a material, and that creates the pattern. And it made sense to me that normal maps should be applied to the material in the same way. So the material defines the sort of base properties of reflectivity, specular, and so on of the surface, and then it has a texture or multiple textures that define the color pattern on the surface, and then it has a normal map or multiple normal maps that define the normal map for the surface. So that makes sense. So in order to implement that, we need to make some changes to materialbase.hpp, which is in the QB materials directory. We need to bring in normalbase.hpp that we've just talked about. Okay, so note that the relative path there. And we don't need to change anything much here. We add a function here to assign a normal map. Okay, so we have void, it doesn't return anything, assign normal map, accepts as input a constant, an std shared PTR of type normal base called input normal map. It's passed by reference, of course. And we have our function to actually perturb the normal, the object normal, to give the material normal. So we have perturb normal that we put in there. Okay, and that, yes, just that. Okay. And finally, yes, here we go. We need to also store the normal maps in the same way that we stored the textures. So we'd simply have an std vector of type normal base. So we create a vector of normal base objects called m_normal map list. And that's that. And we have a Boolean flag to say whether or not we have a normal map. Okay. And one final thing, we want to store the material normal at the current point. The stars here, look, are just to remind me that this is the code I want to talk about. Don't worry about those. And yeah, so we have create a public member variable called m_local normal that we're simply going to use to store the local normal at the current point. Okay, so that is everything for materialbase.hpp. Let's look at what changes we need to make to materialbase.cpp. Okay, materialbase.cpp. Not very much to change here. Now, let me see, where are we? So, first of all, we have our function to assign a normal map, of course, that we've just talked about, and all it's going to do is use the pushback method to push back the input normal map into normal map list. Simple as that. If we have at least one, then we set the m_has_normal map flag to true to tell us that so that we know we have at least one normal map defined. That's it, very simple. And finally, we have our perturb normal function here. It accepts as input the normal that we want to perturb, the UV coordinates of where we are on the surface, and our up vector. Okay, so we copy the original normal. We then perturb it by simply calling the compute perturbation function for that particular normal map list. Now notice what we're doing, because we can have multiple normal maps defined. You'll notice that this is looping through everything here, looping through all of our normal maps and applying this progressively. So it'll apply the first perturbation and then the second and then the third and so on consecutively. Okay, and then simply returns the new normal. Now, one point to note, actually up vector is accepted here as an input. It isn't used anywhere because that's legacy. I should have deleted that before making the video, but never mind. Apologies about that. It doesn't actually affect the functionality. So note compute perturbation, as we talked about when we looked at the base class for the normal maps, it decides what up vector to use itself depending on the direction of the normal. So there we go, don't worry about that. Okay, that's all the changes that we need to make to materialbase.cpp. So lastly, to actually do this, we need to implement it into a material, and I'm building everything into the simple material class, which is the base material that I'm using for everything. So changes that we have to make here, this is in the material base header file. Nothing actually. So simple material.cpp, let's have a look what we have to do here. So we have everything. So the first thing that we have to do is in our compute color. So the compute color method is the method that computes the color of a point, any point on the surface of the object from the material. And it deals with everything. We talked about this before, the diffuse, the reflection, refraction, everything. Or not refraction, sorry, that's a different one, but reflections and diffuse and specular. Right. But the first thing we need to do is disturb or perturb the normal if we have a normal map. So if we have any normal map assigned, then the first thing what we first do is we copy local normal into new normal. If we have a normal map assigned, then we are going to we do declare an arbitrary up vector there and pass it, but we're not really using that. And then we simply call the perturb normal method, and we pass to it new normal and the current UV coordinates for the object that we're looking at and the up vector, and that will give us new normal. And then simply we then store that into m_local normal. So that's really useful if we ever want to interrogate the material later from outside of this class, then we can identify what the actual local normal was at a particular point. So we can already do that for the object itself, and then if we want to know what the perturbed normal was according to the material, we can extract that as well. Okay, so and then I've put a point here that we note the change of local normal to new normal wherever the normal is used in the code below. Because, okay, new normal is now the variable that stores our perturbed normal. So we simply use that everywhere else. Okay, and I'm not going to talk about all this code again because we covered that before in the previous episode when I talked about materials. Okay, that's everything that we need to do there to simple material. So we're almost ready now to see what kind of effect our new normal map can do. the last thing that we need to talk about is the scene class. Okay, so scene.hpp, we need to hash include simplerough.hpp that we've just talked about from the QBNormals directory. And that is everything that we need there. Okay, let's look at scene.cpp. Okay, so scene.cpp, here we go. Yep, very simple. So I've set this up. I'm not going to talk about this. This is basically exactly the same scene that we set up for the previous episode. The only difference here is we declare a normal map. So we're using the same syntax we use all the way through. We have auto norm map is equal to std : make shared. And we create an instance of simple rough, okay, the normal map we've just talked about. And we set the amplitude scale to 0.125. Okay, that's everything that we need to do. So we have a normal map now called norm map. And we then configure our color maps for our textures, we create our textures, and here we are, we create the materials. Now, the floor material we've set up as being a very simple material. It's applied the floor texture, and now I'm using the assign normal map function here to assign norm map that we've just created to the floor. Okay, and that's the only difference that I've made to the scene compared to the previous video. So everything then stays the same. We create and set up the objects exactly as we did before. We push all those back into the scene, and then we have our lights and so on. Okay, so that is actually everything that we need for the code. Let's go to the terminal, compile, run our code, and see what kind of result we get. Okay, so here we go at the terminal. I'm just going to run make so that gmake will then go through and compile all of the code. So let's just run that through. Now, I have tested this before, so there shouldn't be any errors. Let's hope so. So that's materials, textures, and let's see when we get to the new bit, QBNormals, noise, QBNormals there, everything is compiled. Excellent. Okay, so let's just run our code and let's see what we get. Now let that run through. Not the fastest ray trace in the world by any means, but it does get there. And what have we got? Let's see. Bosh, and there we go. So, right, that is the same scene that we had at the end of the previous episode in terms of the textured balls there, but you'll see now that the floor is no longer perfectly smooth. It has now had this roughness applied to it, which is pretty much exactly what we would expect. So we have applied at every single point here a random perturbation to the normal vector for the floor, and you can see that the effect that that has, and that is very, very simple, but it is already starting to be a little bit interesting. And let's just play around with the variables a little bit. So if we go back to the scene class where we created this, so we're creating our normal map and we set our amplitude here. Let me just show that it does indeed work. If we set the amplitude to 0, now let's go back to the terminal and compile again. Right, so rerun make. The great thing about using gmake, it only compiles the code that has changed, so that's very useful. That's why I use it. And let's run .qbray again. Okay, and there we go. So with the perturbation amplitude set to 0, we go back to the perfectly smooth floor that we had before. And let's set the amplitude to something quite big because it was really tiny. Let's set it to 0.25. Okay, and let's see what we get with that. So compile again. Run our code. Okay, and there we go. So we see the surface is now rougher. And it doesn't make sense to make the perturbation amplitude too large, especially for a very, very basic random thing like this. I mean, in reality, we would probably never simply use just a random thing like this. So really, you're going to want some kind of gradient noise or something like that, or Voronoi noise, which we haven't talked about implementing to create a more realistic pattern. This kind of completely random at every point displacement is probably sort of less realistic, but you can see it does yield quite interesting results, and I think is enough to really get a feel for how normal maps work and how they can be implemented and the kinds of things that we can do with them, which is pretty much everything that I wanted to cover in this episode today. So I hope that was of interest. What we're going to talk about in the next episode will be how we can actually create more interesting normal maps. And I want to talk about how I created the wavy normal maps that I showed at the beginning, because that's really interesting. They're very sort of simple, still very simple, but it's building up to something more complicated. And then after that, I want to go on to talk about texture-based normal maps. I may combine those two into one episode. I'm not sure at the moment. We'll see how that goes. And then we want to go on to talk about image-based normal maps, because when I talk about normal maps, probably what a lot of people are going to think of is the kinds that you see if you go to any of the online repositories that offer free downloadable PBR textures or whatever. They all come with something called a normal map, which is usually this kind of blue and purpley image. I want to talk about those and how they work and how we can apply those as well. But now that we've covered the fundamentals, we can now go on to talk about all of those things. So hopefully that should be pretty cool. Anyway, like I say, that is everything that I wanted to talk about today. I really hope that's been of interest and that you've enjoyed the video. I had a great deal of pleasure making it. Do let me know in the comments below what you think. And it's always good to hear from you. And yeah, so there we go. Normal maps. Right. Well, as I always say, if you like this video, please do remember to hit the like button, and if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. So the future videos, as I said, coming up, looking more at normal maps and more interesting things we could do with them, you wouldn't want to miss those. Okay. Anyway, that's enough from me for today. So thank you very much for watching. I really look forward to seeing you in the next video. Bye.